Imagine an object so powerful it could wipe the data from every credit card on Earth. Not from a few feet away, but from halfway to the moon. This isn't science fiction. This is the reality of the universe we live in. These objects exist. They are scattered across our galaxy, lurking in the darkness between the stars. We call them Magnetars. They are the most powerful magnets known to exist anywhere in the cosmos. Their existence pushes the laws of physics to their absolute limits. When we think of magnets, we might picture the small ones on our refrigerators, or perhaps the giant electromagnets used in scrapyards to lift cars. But a magnetar is on a completely different scale of power. Its magnetic field is 1 billion times stronger than any magnet ever created by humans. So what exactly is a magnetar? In essence, it is a type of neutron star, but it is a very special, very rare, and very violent kind of neutron star. To understand a magnetar, we must first look at the life and death of stars. Most stars in the universe live relatively quiet lives for billions of years. When a massive star exhausts its nuclear fuel, its core collapses under its own immense gravity. In less than a second, gravity takes over completely and catastrophically. The star tears itself apart in an explosion so bright it can outshine its entire galaxy. For a few weeks it blazes with the light of 100 billion suns. Hidden within this glorious, violent spectacle, something new and extraordinary has been created from the ashes of the star's core. Imagine taking our sun and crushing it down until it is no wider than a city. A single teaspoon of its material would weigh billions of tons. This is a city-sized ball of pure nuclear matter, so dense that protons and electrons have been crushed together to form a sea of neutrons. The creation of a magnetar's field is a process we call the Dynamo Effect. As the proto-neutron star spins hundreds of times every second, the hot convective fluid inside it churns violently. This motion twists and stretches the existing magnetic field lines, strengthening them immensely. Within the first 10 to 20 seconds of the neutron star's life, the magnetic field is amplified to its colossal strength. The result is a magnetic field, a quadrillion, that is a 1 followed by 15 zeros, times stronger than Earth's. It is 1,000 times more powerful than the field of an ordinary neutron star. This immense magnetic field acts as a powerful brake, causing the magnetar to slow down much more quickly than a normal neutron star. All that rotational energy is converted into magnetic power. For a long time, we didn't even know magnetars existed. Back in the late 1960s and 70s, during the Cold War, satellites designed to watch for nuclear bomb tests started detecting strange flashes of gamma rays from deep space. These weren't the gentle, steady signals we expected from distant stars. Instead, they were powerful, fleeting bursts of high-energy light, appearing without warning from random directions in the sky. At first, these gamma-ray bursts, or GRBs, were a deep puzzle. They were incredibly brief, lasting from a fraction of a second to a few minutes, and then they were gone forever. To solve this puzzle, humanity built dedicated observatories in space. One of the most important was the Compton Gamma Ray Observatory, launched in 1991. These repeating bursts were given a name, soft gamma repeaters, or SGRs. The first of these strange beasts was discovered on March 5, 1979. A wave of gamma rays washed over our solar system. By triangulating the arrival times, astronomers could pinpoint its origin with unprecedented accuracy. It came from a supernova remnant in a neighboring galaxy, the Large Magellanic Cloud. The location within a supernova remnant strongly suggested it was a neutron star, the crushed core left behind after a massive star's explosion. But this was no ordinary neutron star. Another piece of the puzzle came from anomalous X-ray pulsars, or AXPs. These were neutron stars that pulsed in X-rays, but they were spinning down far too quickly. In the early 1990s, two astronomers, Robert Duncan and Christopher Thompson, put all the pieces together. They asked a simple but profound question. What if some neutron stars were born with magnetic fields far stronger than anyone had imagined? Their theory was bold and elegant. It proposed that these objects, which they named magnetars, were the source of both phenomena. The magnetar model was a breakthrough. The theory gained widespread acceptance with the observation of the giant flare from SGR 1806-20 on December 27, 2004. The event was so powerful, and its characteristics matched the predictions so perfectly. We had finally found our monster. The strange signals from the cosmic static were the roars and whispers of these magnetic titans. While the magnetar's interior is a superhot fluid, its surface is thought to be a solid crust. The colossal magnetic field puts enormous, ever-increasing stress on the solid crust. Eventually, the crust cannot take the pressure anymore. It cracks and shifts in a sudden, violent event. We call this a starquake. The most spectacular phenomena associated with magnetars are their giant flares. A giant flare begins with a sudden, incredibly bright spike of gamma rays, lasting just a fraction of a second. A vast fireball of superheated plasma expands outwards. As the magnetar spins, this pulsating tail of fire sweeps across space like a lighthouse beam. The mysteries surrounding magnetars took another thrilling turn with the puzzle of fast radio bursts, or FRBs. These are incredibly intense, millisecond-long flashes of radio waves that originate from far outside our galaxy. But in 2020, a clue arrived that was impossible to ignore. On April 28th, radio telescopes detected an incredibly bright fast radio burst from our own galaxy, directly from a known magnetar. At the exact same moment, our high-energy space telescopes saw this magnetar erupt with a powerful X-ray burst. The connection was undeniable. We had caught a magnetar red-handed, producing a fast radio burst. This discovery strongly suggested that at least some of the FRBs we see peppering the distant universe are the product of young, active magnetars in galaxies millions or even billions of light years away. Despite our progress, the list of what we don't know about magnetars remains long and tantalizing. One of the most fundamental questions is about their interior. What is matter actually like inside a magnetar? Another major puzzle is the magnetic field itself. How is it truly structured? Is it a simple, powerful dipole, or is it a complex, tangled web of field lines? We also wonder about their ultimate fate. A magnetar's life is short and violent. Its powerful magnetic field decays over tens of thousands of years. What happens then? Perhaps the most profound question is about their origins. Why do only some massive stars produce magnetars, while most produce regular neutron stars or black holes? A magnetar is definitely not a quiet neighbor. Imagine a planet in orbit around a magnetar. It would be a world living on borrowed time, subjected to forces that defy imagination. When a magnetar unleashes a giant flare, a blast wave of gamma rays would slam into any nearby planet with the force of millions of nuclear bombs. The surface would be instantly vaporized. Over time, the repeated violence of these outbursts could completely destroy a planet, sand-blasting it down to its core, leaving nothing but a ring of dusty debris. This zone of destruction is a stark illustration of the magnetar's power. It is a cosmic tyrant, shaping its stellar system through sheer violence. While a magnetar is undoubtedly destructive up close, its influence on a grander scale can be surprisingly creative. The shockwave from the supernova explosion plows through the interstellar medium. It sweeps up gas and dust, compressing it into dense knots and filaments. These compressed clouds are the stellar nurseries where the next generation of stars will be born. The magnetar acts like a cosmic sculptor, shaping the raw material of the galaxy into new and interesting forms. It can create beautiful and complex structures within the nebula. Furthermore, the connection between magnetars and fast radio bursts hints at a much larger role in the universe. By producing these brilliant flashes, magnetars are helping us map the cosmic web. The immense power of a magnetar naturally leads to a chilling question. Could one pose a threat to us? We have already seen the effects of a giant flare from 50,000 light-years away. If a magnetar were to unleash a giant flare from a few hundred light-years away, the effects on Earth would be significant. It could seriously damage our atmosphere and fry our satellites. The good news is that magnetars are incredibly rare. We know of only a few dozen in the entire Milky Way, and none of them are particularly close to us. The nearest known magnetar is several thousand light-years away, far too distant for even its most powerful flare to cause serious harm. For now, we can rest easy, studying these terrifying objects from a very safe distance. We have journeyed to the very edge of physics. We have stared into the heart of a dying star and witnessed the birth of a magnetic monster. The story of the magnetar is a story of extremes. These objects, no bigger than a city but heavier than our sun, challenge our understanding of the universe at a fundamental level. They are natural laboratories where the laws of nature are pushed to their breaking point. Our quest to understand them has been a triumph of human curiosity. We began with mysterious flashes of light in the cosmic static, unexplained whispers from the darkness. Through decades of patient observation and brilliant theoretical leaps, we unveiled the existence of an object so strange, so powerful, it almost sounds like science fiction. The future of magnetar research is bright and exciting. A new generation of telescopes, both on the ground and in space, is poised to give us our sharpest view yet of these cosmic behemoths. We may even one day detect the faint ripples in space-time, gravitational waves, from a starquake on a nearby magnetar. This would open an entirely new window onto these objects. This continued quest is about more than just understanding one type of strange star. Magnetars are a crucial link in the cosmic chain. They connect the lives of stars to the creation of heavy elements. We are made of stardust, forged in the hearts of massive stars like the ones that give birth to magnetars. The iron in our blood, the calcium in our bones, all of it was created in a stellar furnace. By studying these distant, violent objects, we are learning about our own cosmic origins. The universe is a vast and wondrous place, filled with terrors and beauties beyond our wildest dreams. And we, a curious species on a small blue planet, have only just begun to explore it. The cosmic journey continues, and magnetars, these magnificent, mysterious cosmic monsters, remain at the heart of our quest to understand the universe.